Hi folks, welcome back. So today we're going to go through the surprisingly simple process of designing your own power supply. So this is one of my most heavily requested videos over the course of the channel. I've been putting it off for a little while because I feel like there's already a lot of power supply designs online. So how we're going to approach this is we're going to look at more the steps involved in designing your own power supply instead of just me building a power supply and you copying it. So we're going to be able to adapt this design for any voltage range and any current draw that you want. So first things first, what is a power supply and why do we need a regulated power supply in the first place? Okay, so this is our 9-volt battery. It might start off with an output voltage at 9 volts, but as we use the energy from the battery, the output voltage begins to drop. So with no intervening circuitry, then obviously this change in voltage is going to be passed into our circuit, and we call this issue line regulation. On top of this, as we vary the load, this will also affect the output voltage, causing it to droop, and we call this load regulation. Okay, so this may not seem like a huge issue, and for actually a lot of circuits it's not a huge issue, but if we want to be really precise, which we do, when we're building things like oscillators, we need very stable voltage references, and so we need very stable power rails. So if we don't have these, this is going to cause us a load of problems. So how do we solve these issues? So to make this video beginner friendly, I'm going to use a trusty mains transformer. So this is AC in, AC out. If you want to adapt this to a mains transformer, we'll go into how to design a proper lab bench power supply with all the bells and whistles in a future video. This is meant to be for beginners. So I'm going to build a generic op-amp power supply, plus minus 15 volts. So I'm going to use a 15 volt AC power supply. So let's say you want a 12 volt, like a eurorack power supply, use a 12 volt AC out power adapter. If you want 9 volts, use a 9 volt AC out power adapter. So how do we go about turning our 15, 12, 9 volt AC into 15 or 12 or 9 volt DC? Okay, so what we have to do here is 3 things. So firstly, we need to turn the AC into a varying DC. After we've got our varying DC, we need to pass that through a filter to smooth out the ripples. And then we pass that unregulated DC through a regulator and we get our nice clean 15 volts out. So the first thing we want to have a look at is this rectification circuit. This is a rectifier called a full wave voltage doubler circuit. It looks complicated, but it's actually very simple to understand if we just follow a signal through. Now, all rectifier circuits rely very heavily on diodes. For anybody who's not seen my videos on diodes, we'll do a very quick recap on what diodes are and how they work. So a diode is a semiconductor device that is able to prevent or allow current to flow through it depending on the input voltage's polarity. We see here that if we apply positive voltage to the positive terminal, this shrinks the electric field inside the diode, allowing current to flow. We call this forward biasing the diode. If we apply voltage the other way, this grows the electric field, which opposes the current flow, and we call this reverse biasing the diode. For this video, we're going to assume an ideal diode. This means that there's 0.7 volts dropped across the diode when it's in forward bias, and when it is in forward bias, it looks like a short circuit to currents. Conversely, when we're in reverse bias, it just looks like an open circuit. That's all we really need to know for this video, but for more on diodes, see my sine wave oscillator video, and I even have a whole video going into the physics of diodes if that floats your boat. So the last thing to discuss before we go on to designing the actual circuit is the power coming in. So the AC voltage that comes out of your power brick is going to be specified in a thing we call RMS. So if we've got 15 volts RMS coming out, that's a sine wave with essentially an average voltage of 15 volts. Now to get from the average voltage to the peak voltage, which is what we need to know to design our circuit, you take the average voltage, so 15 in my case, maybe 12 in your case, and divide that number by 0.707. So for the first part of this circuit, we have our input signal and a pair of diodes and capacitors arranged like so. What we're doing here is we're providing 2 paths for current to flow dependent on the polarity of the input voltage. We'll talk values a little bit later on, but for now let's just follow the signal flow through the circuit for 1/2 cycle of the AC wave and let's just see what happens. Okay, so for the positive half cycle first, let's assume that the capacitors start off discharged. As the voltage goes positive, D1 is forward biased because the anode is now more positive than the cathode. Remember, we're going to assume an ideal diode, so we can replace this diode with a short circuit and just remember that we've lost 0.7 volts to that diode drop. The opposite happens to diode 2. We apply a positive voltage to the cathode, so again assuming an ideal diode, we can replace D2 with an open circuit. This effectively removes one of our caps from the circuit completely, so we'll just hide that for now so we don't have to worry about it. Now, this circuit is super easy to analyse. We can see that this positive voltage minus the voltage drop is going to charge C1 to about 20.5 volts. So as the supply turns around and starts to drop, the charge on the top capacitor reverse biases that diode. So this locks the capacitor at that voltage. As we further lower the voltage, we get to the opposite state on either diode. So let's now replace D1 with an open circuit because it's reverse biased, and D2 with a short circuit because it's forward biased. And watch the exact same thing happen to C2 the other way around. In real life, it might take a few cycles to fully charge these capacitors up, depending on how big they are, but very soon we have two capacitors with 20.5 volts across them. It's important to point out that I'm taking this point as ground, which means this negative voltage at the positive terminal causes a negative current, which causes the capacitor to charge negatively on this terminal. Let's see both cycles now for a complete picture. Once we're 0.7 volts above ground, we have enough voltage to forward and reverse bias these two diodes, so we replace them with short and open circuits. This then allows our positive current to flow through the capacitor, charging it up to the supply voltage minus 1 voltage drop. As soon as the supply starts to drop, we no longer have 0.7 volts across this diode, so it switches off, looking like an open circuit again. Once we've swung back to 0 volts, the bottom diode is still off because we need to go 0.7 volts below the capacitor voltage. Once we have done that, this negative current will now flow through the capacitor, charging it to the supply voltage minus 1 diode drop, but this time negatively relative to ground. We can now see why this is a full wave voltage doubler. If we rearrange these components into a bridge, taking the bottom of the bridge as ground, we can see that we've put 21 volts in and we've got approximately 42 volts out. If this was just a standard full wave rectifier, we'd put 21 volts in and we get 21 volts out. Another useful thing about this configuration is we can tap this point off as ground like we did earlier, which gives us a positive and a negative voltage. To do that with this full wave rectifier, you need a center tap transformer and slightly more complicated circuit. So you saw in our simulations there that once the capacitor had charged up, the voltage stayed constant. In a real circuit, we're going to be drawing current from those capacitors. So once they've charged up and the voltage has changed direction, the capacitor is going to drain, and that's going to cause that voltage to droop. We call the difference in that voltage ripple. So this is the ordinary operation of a half-wave rectifier, and our circuit looks a bit like two of these stacked on top of each other as far as the capacitors are concerned. It turns our AC input into a unipolar DC output, so we just bang a capacitor on the output to smooth it out. What we know from earlier is that the capacitor will charge up, and with no load, the output will be held constantly at that peak voltage. But once we attach a load, the capacitor will discharge after the peak of the rectifier sine wave, and the amount the capacitor discharges between the charge cycles is what we call peak-to-peak ripple. It depends mainly on how much current we try and draw from the supply. So in order to calculate the ripple, the first thing we need to know is how much current are we going to be drawing from our power supply. Now you need to know this to design any power supply. So what we're going to do is we're going to base it on our transformer, and we're going to think about how much current can our transformer actually give us. So I have here a 22 VA 15 volt RMS transformer, right? So that's a load of gobbledygook. So basically if I take my 22 VA, divide it by 15, that gives me 1.5 amps RMS out of this thing. Now I've seen a few videos and schematics based on this design that make the valid approximation that your DC load current is approximately equal to your RMS current. Now for this voltage doubler design, we can't necessarily make that approximation, and I'll talk about that in a minute. But basically people see the 1.5 amps RMS and think, right, so that means I can draw 1.5 amps DC. For this design, you cannot do that. You've got to take the current rating and divide it by about 3.5. So for my 1.5 amps, that means I can draw a maximum of about 450 milliamps. And I'm going to go a little bit underneath that and go for 400 milliamps, which gives me 200 milliamps per rail. So why we have to do that is because of this thing in rectifiers called the conduction angle of the rectifier. We have a catch-22 here where we need to reduce the ripple voltage, so we put large capacitors in there. But because we've reduced that ripple voltage with our large capacitors, And if we're drawing lots of current, we need to shove all of that charge onto the capacitor only in the period above the ripple voltage. So there's this tiny window, which is only a fraction of the cycle of the sine wave, where we have to shove all of that charge onto the capacitor, and the rate of flow of charge is current. So essentially what happens is we get these big spikes of current that are way, way above our 1.5 amp threshold if we're not careful. So this can cause your power supply to do funny things. Best case scenario, your transformer is going to heat up and fail early. So because we're making a simpler design that uses one of these power bricks, these don't have a center tap in their transformer, so we can't do a proper full wave rectifier. Because of that simpler design, this is the drawback. There's always a trade-off in engineering. And as I said, in a future video, we'll do a proper power supply design for a bit of a beefier power supply. So let's take that 200 milliamp figure and calculate the ripple voltage. So when we charge or discharge a capacitor, it follows this possibly scary looking, but actually quite simple equation. What this animation shows is that the size of the capacitor affects the ripple voltage. Feel free to pause and go through the maths if you're interested, but all I'm doing here is rearranging this equation so that we get the amount of ripple in terms of the DC load current and the size of the capacitor. So I've done the hard work for you here, and we now have this really simple equation that will help us pick the right capacitor. What we can see from this equation is that a larger current draw is going to discharge the caps quicker, giving us more ripple, and we can combat this by increasing the size of the capacitors. So I'll be using a linear regulator IC for this design, and most of these regulators, you can't let the ripple voltage fall below 2 volts above the voltage that you want your output to be. So if I'm making a 15 volt regulated supply, my positive rail can't go below plus 17 volts. If you're making 12 volt regulated, your positive rail can't go below 14 volts, for example. So I'm going to add a half a volt to accommodate for like tolerances of my parts. And also there's a current limiting resistor in the filter network, as you can see in this little schematic. And so we're going to size that resistor so that there's no more than a volt dropped across that. So we've got 15 volt RMS, which is 21.2 volts peak. We lose 0.7 volts to our diode, which gives us an allowable ripple voltage of 2 volts. So as we said earlier, we'll design for the worst case load current of 200 milliamps per rail. So all I need to do is rearrange this equation one last time to give us the minimum capacitance we need per rail. So I've gone for 1000 and then doubled it up in the filter stage for a total of 2000 microfarads per rail. Just be sure to use capacitors that are rated for the appropriate voltage across them. So you want to size this to drop no more than half a volt, say, across it. I've gone for 1 ohm here. And remember to use 1 watt or better resistors. Okay, so our last step is to just wire up this linear regulator. So I'm going to use the LM7815 and 7915. If you're doing a different voltage, you can just replace those with the appropriate regulator. So 7812, 7912 for 12 volts and so on. So these want filter capacitors at the input and at the output. So just something small like 100 nanofarads, 0.1 microfarads. And we're going to put some diodes in for safety. So these prevent latch up, which is basically a temporary short to ground can become permanent if you don't have these diodes in place. And these other diodes are a little bit more subtle. These will basically short circuit the regulator when you switch the power off. So when you switch the power off, there might be a period where the input voltage drops, but the output voltage is held constant by the capacitance at the output. You know, we don't know what you're going to be connected up to. And these regulators do not like being reverse biased at all. So if the input drops below the output, these diodes will short circuit the regulator so that they don't get damaged. So the regulators themselves are a bit of a crazy, spooky mystery box of magic. So why don't we just do a very quick segment looking inside the regulators and figuring out how they actually work. So this is what's happening inside these regulators. It's essentially just a series pass transistor in the feedback path of an op-amp. So I could talk through all the theory, but I think it's easier if we just follow a circuit through. But let me just point a few things out first. The first thing to note is that we've got a Zener diode here. This is a special type of diode that we can essentially just think of as a voltage reference. So whatever the input voltage, we'll see, let's say 5 volts across this diode. So this is going to set the voltage at the non-inverting terminal of the op-amp. So the next thing to realise is we've got negative feedback. And so with negative feedback, the op-amp's output will do its very best to make the 2 inputs the same voltage. So now all we need to know is how to set these output resistors, and we can walk through the circuit. So remembering we've got a 5 volt reference and we want the output to be 3 times that. Let's take it for granted that the op-amp will force enough current through R2 to drop 5 volts across it, because this is how the op-amp is able to make the 2 inputs equal. We then just need to make that top resistor twice that, so we can get 10 volts dropped across that, giving us 15 volts at the output. So let's see what happens when we apply our unregulated input signal. All that's going to happen is the voltage is going to ramp up until the 2 inputs are equal, and then the op-amp will hold the voltage at that point. So if we draw lots of current from the output, this starves the output resistors of current, drops the output voltage, and then the op-amp is able to just drive the transistor a bit harder, supplies more current to raise the output voltage back up. If you want to know the details about these types of circuits, I've got a whole playlist on transistors, and I've got a whole playlist on op-amps as well up in that top right hand corner. So let's have a look at this finished circuit now. Okay, so here's the finished circuit built up. If you want to watch me go over this and go over the testing rig that I'm going to build in a moment, then check out my Patreon only video where I go over all the buildy, boring details in a lot more detail. So I've got some 1000 microfarad capacitors, and I've got some 1 ohm resistors in here in this kind of filter network, going into these 7.8 and 7.9, 15 voltage regulators, and then I've just got these come out and put on the rails of this breadboard just for testing. And if we have a look on the oscilloscope here, so the first thing we want to do is check these voltages. So you have to power these up under some load. So I've just got 1k resistors in here just as a light load. And as well, when you build up your circuit, I've not got any output capacitance, which you will want, and I've not got any output diodes as well, which you will want. This is just for showing you these voltages. So let's have a look on the scope. We can see this is my transformer secondary, so it's looking quite saturated. That's not unusual for these cheap transformers to saturate a little bit like this. I think mine's probably a bit worse than you'll see, because the UK nominal voltage is 230 volts, but the voltage that I'm actually getting out of my wall is like 245 volts-ish. So that's making mine look worse, but it's not uncommon to see these cheap transformers saturated like this. But importantly, what we can see is we've got a nice steady voltage at -15 and a nice steady voltage at +15. So let's test this out. Okay, so now what we've got here is I've set up these 2 MOSFETs with some resistors here and just a simple op-amp as an active load, so I can now electronically control the current draw out of this. This dark blue trace is the output of the rectifier. So we can see here there's a tiny little bit of ripple voltage because of our minimum load that we've got it powered up under. So let me just adjust the load and we're going to see how the circuit reacts. So what we'll see is the ripple voltage increasing as I increase the load. And so this is at about full load. So you can see that that headroom that I designed into the circuit was a good idea, because it means the circuit is still performing quite nicely even under full load. We've got a little bit of spare room, which you always want. And so just as we saw on our simulations earlier, capacitors are charging up in this short period here while the transformer voltage is higher than the capacitor voltage, and then it's discharging throughout this entire period. So this is what I mean by this conduction angle. You can see of this entire cycle, if we say the cycle lasts from here to here, it's only this tiny fraction here, it's about 1/10 of a cycle in which it can actually charge, and so it has to shove all that charge in over that very short period, and that's where we run into problems. So let's just see what happens as we increase over full load. As we start to approach the cutoff voltage, which is 17 volts, which is about here, we'll see the supply start to fail. And there it is, you can just see that, just there, the supply is failing to maintain that 15 volts, and we can go quite extreme with that. We can see that essentially how these regulators work is as long as you keep the ripple voltage above that threshold, about 17 volts, then you should be good. Okay, so the number one factor is the impedance of your transformer, your wall mount power supply. So if you're finding that your supply isn't working how you intended it to, then that probably means you're trying to draw too much current. It's not trivial calculating the RMS current draw out of these wall mount transformers. So if in doubt, draw less current. So as I said, in a future video, we'll go over something that can be a bit beefier in terms of current draw. I would say this design isn't ideal if you want to draw anything more than a few hundred milliamps, 300-400 probably as a maximum. So these linear power supplies are great. Low noise, low ripple, super reliable, The only big downsides are excess power dissipation. You know, that to regulate the voltage down, we essentially burn that excess power off as heat. And as we mentioned earlier, the lack of a center tap in our transformer limits the amount of current that we can get out of a similar sized transformer. And as I said, we'll go over that in a future video. So I'll be uploading a companion video to this one, going over the build itself, going over that testing rig I built, going over some little troubleshooting pitfally bits, and just generally going over the finer points of putting this circuit together. I generally upload extra stuff onto my Patreon for my patrons, you know, extra design points, extended versions of videos, answering patron questions, doing regular Q&A videos and other things like that. And just generally, it's the best way to support me as a creator. So if you like my videos and you want to help support me to make more, then please consider going over to Patreon and supporting me there. I'll be incredibly grateful for it. If you can't support me on Patreon, then make sure to subscribe, leave me a like and a comment, share it with your friends, and most importantly, come back next time where there's plenty more synthy goodness to be had. And I'll see you then. Bye bye.